They can be found already in the displays of mobile phones, OLEDs, organic light-emitting diodes. Their importance will grow further in the future. Existing technologies in lighting systems will gradually be replaced by OLEDs. A closer look at an OLED display reveals that the pixels are made up of 3 colors, as in classical LCD displays. These 3 subunits emit blue, green or red light. Superposition of those units generates other colors. Let us have a look at a cross-section of the green organic light-emitting diode. A transparent material serves as the carrier. The individual layers are applied in a vapor deposition or printing technique. The first layer is the anode, the so-called hole injection layer. Blue stands for the so-called hole transfer layer. The emitting layer is then built up on that layer molecule by molecule. On top of the emitting layer, the electron transfer layer can be seen shown in gray. Finally, the entire OLED component is completed by the cathode. A voltage is applied to the component. Now electrons move from the cathode and holes move from the anode into the emitting layer. Where holes and electrons meet, photons, that is to say units of light, are released. As in many areas of organic electronics, it takes a large number of experimental attempts to produce an optimum OLED. In numerous tests, research scientists and developers produce prototypes and test them. This is a process consuming a lot of time and money. At the Institute for Nanotechnology of the Karlsruhe Institute of Technology, scientists have now developed a software which is able to simulate this process in a computer. The simulations of SiMona are carried out in large computer centers. The scientists use computer calculations to look for suitable dye molecules and optimize materials' properties. Compared to the time-consuming, real-scale experiments in a laboratory, SiMona is a precise method saving both time and money. The electronic properties of and the transport of charge carriers in a material are imaged virtually and optimized by SiMona. The basis are high-resolution morphology predictions and quantum mechanical calculations. This is a split-screen view on the left, before optimization, on the right, after virtual optimization by SiMona. The packing density of the emitting layer is compact. Mobility of the charge carriers is high. The quantum yield is uniform. Virtual optimization is used by scientists to derive the molecular structure as well as important parameters for producing real OLEDs. These data are then used to make a prototype. Displays of the future can be manufactured on moldable carrier materials. The result are flexible screens which can be rolled. If this technology is to be cost-efficient, materials must be optimized virtually prior to production. This is where simulation software such as SiMona plays a key role.